Mic check. Morning. I can see a few of you here. Morning, I see you. Glazer, Killer Pear, Tyler, good morning. How's everybody doing today? Hopefully well. Morning, everybody. We're having a cold front. I don't know if you guys are having a cold front, but we're having a cold front, which is why I'm wearing a thing to keep myself slightly warm. I'm enjoying it. So if you're having a cold front, I hope you're enjoying it. It's morning. Oh, freezing. Yeah, so I mean, for me, it's nice to have a change in the weather and a change in the seasons. I always enjoy that part. Maybe less so when the summer arrives, but certainly when the fall and winter come, I like that a lot. Okay, we are in week 12, and I'm gonna just give you a heads up about a coming week here before we do week 12 stuff. So much of what we're doing for the rest of the semester is going to be realized in your second individual project. So every week we're adding new tools and techniques that will help you bring together the bigger individual project too. At a glance, it looks big and scary, but if you build it by the pieces that we get each week, then I don't think you'll find it nearly as intimidating. But I want to point out to you week 14 in particular. So we're in week 12. Next week is week 13. The week after that is week 14. I'm going to click on that just to give you a heads up. So week 14 doesn't have any of the usual content in it. So I'm going to lecture that week. That's the week of Thanksgiving. I'm going to lecture that week, but what we're going to talk about is focus on, okay, let's start building the second individual project and see what pieces we have, what pieces we still need to build that project out. If you're taking both this class and Programming Algorithms 2, then hopefully that gives you a little bit of relief around the week of Thanksgiving. If you have Thanksgiving work or events that you do, hopefully that helps you a little bit. But just note, week 14 does not have a discussion, it doesn't have a lab, it doesn't have homework, it's just a lecture. That's the whole week. So hopefully that helps relieve the pressure for some of you who have at least the two classes that I do that have a heavy workload. Okay, week 13 will be normal. Weeks 15, 16, and 17 will be normal. But week 14 is a little bit of a one-off. Okay, what are we in? Week 12. So we're doing addressing modes more. So a lot of you did that was a good discussion, so I appreciate that. Somebody pointed out that you can see direct addressing sort of in a standard variable in a high-level language. How pointers are indirect addressing, and also how arrays are indirect addressing. Hold on, I'm getting a tea. Does that have honey in it?
Yeah.
Thank you. And now this week we're going to add the x86 assembly features that allow you to actually address array-like things in memory. Okay, yes you can. So the question is, I don't know what C. Oh, you mean, okay, so comp sci 21. No, so our comp sci 21 at Butte College is just Programming Algorithms 2. It's not robot related. It's just sort of standard computer science. We do data structures mostly in that class. So no, we don't talk anything about using C++ for robots in comp sci 21. Yes, it's a data structures class. Okay. So, goals for the week. So we're adding a couple more addressing modes. You're welcome. We're going to add how do you access array-like things in memory, and then use HLA programming to explore how those things work. I need to fix my display because I want to put Notepad++ back up if I can, and put some notes in here. So addressing modes. So we have direct, we have indirect, and now we're adding indexed and scaled indexed. These addressing modes are the ones that allow arrays to work in high-level languages. The idea of indexing is that you go to a memory location and then you compute an offset from it. You're used to calling these things indexes in high-level programming, but technically what they actually represent is an offset. So you'll see that in code anyway. So these are the two new x86 addressing modes that we're adding. Indexed and scaled indexed addressing. That you can do in x86. Okay. And then that will allow us to start working with arrays. And arrays in HLA are very similar to what you're accustomed to. The thing that looks intimidating about the second project is that we're not going to use static arrays, we're going to use dynamic arrays. But at the end of the day, it turns out it doesn't change the underlying code because all we need to work with an array is the address of the array, and we can do everything else that we need. So a couple of readings, and again, these are sort of focused down into specific sections of the text. So the reason why we're doing arrays this week is because arrays is the best way to explore indexed addressing and scaled indexed addressing. The homework, same as always. I'll give you a tip about this, so you might want to note this. A lot of the answers in this week's homework are effective address. So I'm not trying to trick you with those answers. I'm trying to drive home the point. So if you think the answer is effective address, as you can see in the notes here, it probably is effective address. So I'm trying to drive that point home a whole bunch, because it's in my opinion, the most difficult thing about the second project is getting effective address straight in your head. So we're just going to hammer away at what do I mean by effective address, what do I mean by effective address, and we're going to start with that today. So if you find that answer coming up more than you feel comfortable with, that's not because I'm trying to make you uncomfortable, it's because I want to really drill it into our heads what we mean when we say effective address. You need to understand this concept for this class, but it also helps you understand how arrays, as you experience them in high-level programming, actually work, and what added sort of benefits you're getting from high-level arrays typically. Come back to the lab in a second. So the discussion seems like a long one. But again, it's because part of the goal of this class is to have you look at how the processor actually does something and then map that into a high-level language that you might use. And with the hope being that you're a better user of C or C++ or Python or Java or whatever it is, that you'll actually be a better programmer in high-level languages if you understand what the processor actually has to do underneath. So this week we're doing arrays and array addressing modes in x86, and the discussion prompt is asking you to pick a language and go look up a couple of the array features of that language. So someone's going to fetch C++ right off the bat, but you might sort of challenge yourself to go look at a different language. And I'm going to give you a note about that. So if you Google Tiobe index, I don't know if that's how you say it, but it makes me think of, what's the character's name, Niobe in the Matrix? I think probably it's Tiobe index. If you Google Tiobe index for the discussion prompt, This is information that you might be interested in. It's a programming languages popularity index, and it's continuously updated. So they have their way of measuring what makes a programming language popular or important, but you can kind of tell what languages are being widely used. Java's way up there because of the Android system, even though I expect it's going to drop because there's a new language on Android. But look, C has somehow clawed its way back to the top. So anyway, for this week's discussion, you might Google the TIOBE index and then pick a language from that top 20 and go look at how arrays work in that language. I'll tell you, let's see, well, C is pretty obvious. Python, C#, we have someone who knows C#. Shockingly, Visual Basics, it's still on the list. JavaScript, PHP, R is very popular with data analysis people and machine learning people. SQL I don't really think of as a programming language, but whatever. Anyway, just an idea that can help you find a language if you're doing the discussion prompt this week is to use the TIOBE index. All right, so let me get to a couple questions here. Yes, so arrays, in computer science, an array is a contiguous block of memory. That's all it is a contiguous block of memory. So that's true, Captain Price. When we say array, we mean a contiguous block of memory. And because it's contiguous, it makes it easy to compute the addresses of specific elements in the array, because we start at what we call the base of the array, and then we compute an offset to the individual element of the array. Yeah, so why is the C language still on top? My guess is the C language is still on top because it's still an important systems programming language. So if I am creating, for example, the machinery of a machine learning system, underneath I'd probably use C or C++, even though on top I might use Python for developing the individual applications. I might have the actual machinery underneath in C, but operating systems are still written in C. I would bet you, for example, that the PS5 and the new Xbox, their operating systems are probably written in C. Linux is written in C. So it's still sort of the important systems programming language. Now, why it's risen to the top recently is something happened in the world where there's a project or a development that's popular right now that people are using C for, is typically what happens. Yeah, Microsoft uses C all the time. So yeah, these things. And my favorite languages, by the way, are down here sort of in the sad list. So you can get deeper in the list. Here's 21 and on. So let's see, what do I use? I like Scala. Julia is rising in popularity with the math people. I like D, but no one's ever going to use it, I bet. Kotlin should rise in popularity because you can now develop Android applications with it. Ada is popular in like automotive programming. We don't even have my programming language yet. So here's the also-rans, and I bet my languages are in here. Clojure is in here, Elixir's in here. Yeah, it's kind of sad for them. Anyway, you can, this is an excuse. You can use the TIOBE index to see what languages are popular, but also then go look up how do they do arrays in Groovy, which, by the way, has the coolest name, I think, doesn't it? Yeah, Bash is in the also-rans list somewhere, isn't it? Or is it way down here in the barely even registers list? Yep. Barely even registers list. That's a bummer. I like Bash. Okay, so anyway, got off on a tangent there, but that's just to help you with the discussion prompt, so that if you don't know, I don't even know what languages are out there, the TIOBE index can help you. And also, it's just interesting to monitor the TIOBE index They have competitors, by the way. There are other programming language popularity indices. That's just one of the more established ones. Okay, and then last is the reminders. So homework lab discussion this week, and then in theory, you actually have the tools to do something that you can look at an individual project to this week. And I'll show you my ideas for doing that. Okay, so I think I'll load up the lab. Actually, let's switch, and I'll just do some basic array type of stuff so you can see where some of these ideas come from. I'm going to have to switch the view so that you can see. Okay, so before we get into the lab code, let's just go talk about how arrays are done and what they look like. Yeah, we still teach Bash in our Linux class as well, even though a lot of people will use a language like Ruby to write shell scripts anymore. I use Bash all the time just for simple stuff, just to automate things like on web servers and stuff. Okay. Hopefully you can see. If you can't see, holler on chat. Okay, I think you can see. Let me squish that so that everybody's visible. Okay. So before we get the messy lab code, let's just do a couple of samples around arrays and talk about the addressing mode issues associated with arrays. Well, if you're to the thing about cheating by sending commands to your, I don't think it's cheating if you're figuring out how to use technology to explore how a thing works or to interact with it. It's a way to develop skills. And, I mean, I guess if you're cheating people out of money, that would sound different, but if you're just using your technical skills to interact with the system, I think it's kind of cool. Okay. So I'm going to make this little array examples file. And it never picks up HLA the first time. I'm going to go tell it. Oh, here's another place where you can look at potential programming languages is in the text editor's syntax highlighting. Okay, so it is important to note that arrays are in contiguous memory, and what we mean by that is that they are back to back to back to back to back. And we can actually compute the addresses of all of them, which I'm about to do. So let's make a num8s array. So that's going to be an integer array. Let's just do 5. Now I think they're all zeros if you do it this way. So we're going to make static arrays, and I like HLA because it's obvious that it's static because it says static. So what that means though is that I have space for 5 int8s back to back to back to back to back in RAM. So good question. Does 5 mean 5 spots or 6 spots? 5 means 5 spots, which is true in every language. When you declare arrays, you say how many slots that you want, and then computing offsets or indexes comes after that step. So I've got 5 int8s. The indexing starts at 0, that's true. Same in HLA, but you still, when you declare an array in C++ or any other language, you tell it how many slots you want, and then the indexing problem comes second. I think in Visual Basic maybe you can change the index, or it indexes from 1, which is just weird because no one else does that. Yeah, so the highest index value here would be 4. Okay, so that's an array, and it is important to note that this is really 5 int 8s in contiguous memory. And I'm going to print all their addresses here just for fun. So I'm going to grab the address of the first one. That's the first one. The first one we call the base address. I want squares. Or we might call that the 0th element, the element at, that's going to be hex, at index 0. I'm not going to do that, but you can do 4-dimensional arrays, although I never would because I would get lost in them so quickly. But you could do it. Okay, so first concept here. The first element of an array appears at the base address of the array. So when you access, and I'm going to use indexing also, when you access elements at index 0, all you're really saying is, I want to offset 0 amount from the base. So if I go to the base address and I offset 0 amount, I get the first element. That's just how it's going to work. Actually, I'm not going to do the new line yet. No, I am. I'm going to do the new one. I'm just lining these up because I want to. Is num 8s at index 0. So I'm going to print out the address itself, which is wherever it is, and then I'm going to use the array label as a base address and then offset 0 elements from that, which gives me the first element. I am going to need an include. Thank you. Good catch, Captain Price. Oh no, Glazer. Sorry, Glazer caught that. Yes, thank you. I was going to get a compiler error and be unhappy. Good catch, Glazer. Thank you. Okay, so the first element is at the base of the array. So I'm going to get the address first just to show you what the address is. It is whatever it is. And then I'm going to show you that if the standard way of using arrays is the label, which is the same thing as saying the base address of the array, and then an index, or more technically an offset. So if I go to the base, which is represented by the label, and I offset 0 elements from that, that gives me the first element. And I'll go ahead and run that. It should be 0 to start, and then I'll populate it with some stuff. So it's a 0. It wasn't spaced. Oh yeah, there's an extra space here. And it's 0. Okay, so you can also pre-populate arrays in HLA. So now I'm going to make the first element be 10. All right, let me pick up a few questions here. We are going to end up using the stack. So yeah, we'll probably do that in my sample here, is use the stack. No, the stack, so the stack will be a completely separate structure. And so the question is, does this array have any kind of precedence relationship with the stack? Is one of them more important than the other? And the answer is no, they're of equal precedence. That's totally a matter of how the programmer uses this array versus uses the stack. So they're completely separate entities. The stack is built in, and the array I just created in RAM separately. Although the stack is in RAM, but it's a completely separate entity, and the only way to make them appear to have any precedence is if I program one to be more important to me than the other. But otherwise, they're completely separate entities. Okay, so I populated the array with data just to show you that when I print that out, There's the 10, that's the first element. And then I'm going to do this. So what is happening here? If I add 1 to EAX, I'm taking this address and I'm moving over 1 byte. And you're going to see that when I print these things out. So let's do the base separately, and I'll put an extra new line in. Okay, so what I want you to see here is that I'm going to take this address and I'm going to shift it over by 1. And we'll change the code around here in a second. If I do this though, if I move this base over by 1, I am now at the second element of the array. Now typically what we do and I'll say I'm moving it over 1 byte. So if I move this address over 1 byte, I get to the second element, which typically in high-level languages we print out like this. I'm going to switch this around and say element 1. Okay, so we're going to change this up in a second, but that is go to the base and move over 1 byte. So that's super, super, super important actually that you understand that in the processor, in x86, moving around or offsetting into an array is actually computed by the number of bytes that you move, which you're going to see that in a second. Okay, so question. When we don't populate the array, why isn't there garbage values? And the answer is because in HLA, the HLA language actually zeroes out your memory for you if you haven't given values for it. So that's a feature of the HLA language, that it zeroes out your values. C++ does not do that. The Go language does do that. So different languages do that differently. In C++, if you don't initialize an array or a variable, you get garbage. But in HLA, you get zeros if you don't specify the values otherwise. So that's why that happened. Is it's actually a feature built into the HLA language. Okay, so here I'm moving over 1 byte. And you can probably imagine what happens from there, but let me spin that up. So there's the 20. I want you to notice that the addresses are actually in hex 1 byte different. So here's where the first element lives, and if I move over 1 byte from there, I get to the second element. And if I move over 1 byte from there, I get to the third element, and so on. 1, 2, 3, 4, 1 more, right? 1 more. So I'll add 1. So this one is 2 bytes over from the base, 3 bytes over from the base, 4 bytes over from the base. Should give me all of my values. So this is different from high-level languages, which you'll see in a second. Because I'm going to change this array to be something else. Let me clear that first. Alright, so there's all the values, and notice that their addresses are actually 1 byte apart from each other. And that's because they consume 1 byte. So let's make a change to this code and watch all hell break loose. So let's change these to int16s. And I'm going to bump up these values just so it's easier to see. And I'm not going to change anything else, but something's going to be terribly, terribly wrong. No. That. Okay, so the first one was okay. But you notice, like, Well, it should have been 100 followed by 200, followed by 300, followed by 400, followed by 500. And yet for some reason, I'm just getting the 100 and then garbage, and then 200 and then garbage and then 300. So the question is, so the 100 section works just fine. If I go, I shouldn't call them num8s, but I did. If I go to the array and I don't move over any at all, I actually get my 100 value here. But something is wrong in this second section because I get garbage. So your challenge is to figure out what is wrong. Good one, Captain Price. So in 16 are 2 bytes apiece. So I need to fix all of these lines. So let's start on line 14. What has to change? If my array is now 2 bytes a pop, what has to change on line 14? It didn't allocate garbage. So this did not allocate garbage. I'm accessing the wrong stuff. So we'll fix these and then we'll sort of look at what happens, and then I'll undo and I'll go back to the original one. So something's wrong here. When I change this to N16, these values, which should be there, are no longer there. So they're not garbage, it's something else. Okay, so we need to move over 2 bytes at a time. So every element is 2 bytes apart from the element before it, and then there's something wrong on this line as well. You don't have to do the whole line, but there is something wrong on this line. Not quite. I'll zero in on it. Something's wrong here. 2. So on the processor and in HLA, this index is not the element that you want. It's how many bytes over you need to move to get it. So to get the second element, I have to move 2 bytes over from the first element. Index 1 doesn't exist. Index 1 is actually part of this first element. So you have to learn, and that's why we're doing it this way, you have to learn in HLA that these indexes don't mean which element, they mean how many bytes since the last one. So the first element is 0 bytes from the start. The second one is 2 bytes from the start. The third one is how many bytes from the start? 4 bytes. The third one is 6 bytes over, and the fourth one is 8 bytes over. Now all of these are moving. So the processor works this way as well. On x86, when you are addressing array values, you have to compute the offset starting at the base address plus the number of bytes to move over. So I'll put a note here on index is the base plus byte offset. So one thing that you're getting for free in C++ is that C++ is automatically figuring out when you say index 1, C++ already figures out automatically for you how many bytes that means, which is kind of cool. So what's happening, I'll get my machine back up, what was happening when we were getting errors, and we'll look at that, what was happening when we do I am starting at the base and I'm moving 1 byte over. Yes. So Glazer asked if we were doing 32-bit values, would we have to be offsetting 4 bytes at a time? The answer is yes, that's precisely right. And we'll do that just to close the loop on this, but you're exactly right, Glazer. If we make this int 32, you sort of have to understand that you have to do the byte calculations in your head. It's probably bytes because it's for backward compatibility and historical reasons that it's just always bytes. So on x86, when you are computing array offsets, you compute them by the number of bytes, which can be a pain in the rear because it's so easy to forget. All right, so what's happening when I print nums8 at 1? We do. So Gersovax asks, do we have doubles or floats? And we do in HLA. So in week 17, we're actually going to look at the floating point numbers. In HLA, we call them real. So you'll see there's a real 32 and a real 64 and I think a real 80. So they call them real numbers, the data types in HLA, and they do have them. We're just avoiding them because you'll see in the last week, floating point values are crazy on the processor. Like nothing like you may have even imagined that they are. They're pretty neat. Okay, so what's happening when I print nums8? No, you can't. In the output, you can. So Captain Price asks, can we specify a number of decimal places? You can when you're doing outputs, but you can't in terms of how the processor stores the floating point value. It's a consequence of the way the circuitry does the arithmetic for computing how to store a floating point number. They're quite strange. We don't do them until the last week because they're just super weird and difficult to work with. Okay, so I'm going to close the loop on this. So what was happening there when we were printing nums8 at index 1? Well, what we were doing is we were printing nums8 1 byte over from the start. So one thing to imagine is what's at nums8 0? Or num8's at 0. It has the value 100 in it as an int 16. So it looks like, nope, 1, 2, 3, 4, 1, 2, 3, 4. So let's put the value 100 in here. So 1, 2, 4, 8, 16, 32, 64. And 32 is 96, and then I need 4. So that's the value at nums 800, and then it's followed by a 200, which is 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 4, 1, 2, 4, 8, 16, 32, 96, 64, 128. So there's a 128, which leaves us with 72. So there's a 64, which leaves us with 8. Something like that, I hope. So here's the thing to think about in our array. If I do nums at 0, the whole 16 bits of it are these bits. But if I do nums8 at 1, it actually moves over past this byte and grabs 16 bits from here, which is kind of crazy. But when I move over 1 byte and I tell it that the array is 16 bits, well, it's going to start where I tell it, and then it's going to grab 16 bits, which is a now crazy large number, which was, I may not have computed it right, but it gets negative 14,336. So the point is, if you move over 1 byte in an array of 16-bit values, you end up getting part of one value and part of another all mixed up with each other, which is why you get weird outputs. So that was what's going on there. I don't know if that makes sense, but when we did nums8 at 1, we moved over a byte from the start, and then we grabbed the 16 bits because we told it to grab 16 at a time here. But we told it to grab the wrong 16. So that's why when we grab from 0, then we have to jump 1 byte, 2 byte, and then grab from 2 bytes over. Pretty freaky. Okay, so let's do it for 32 just so we get the idea straight in our head. So if I make it 32, so here's a sort of a quiz question. How many bytes is this array? Like how many total bytes does it consume in memory? I lost my insert key at some point. That's interesting. 20 bytes. Outstanding, Captain Price. So to compute how many bytes it actually consumes in memory is the number of elements times the size of each element. So this is 5 4-byte elements, which is 20 bytes. Okay, so the first section doesn't change, the base doesn't change, and accessing the first element doesn't change. Now that we have a 32-bit array, we're going to be moving over 4 bytes at a time. And then what's the fix for these guys? So line 20 now is wrong because I'm not offsetting the right number of bytes. That one's 4, good one. Second one, line 24. Eight. My numlocks key came off. 8. Yep, good one, Cursive X. So the first one's at 4, the second one's at 8, the third one's at 12 bytes over. So you have to move across 3 whole 4-byte variables, basically. And then the last one on line 32 is 16 bytes over from the base. So the point here is that in HLA and on the x86 processor, you have to think when you're talking about arrays in terms of bytes. If I have an address of an array, how many bytes do I have to move to get to the part that I want? Pretty crazy. I'm going to move this to the side, and let's just use addresses now. Do I need all of it? Yeah, I'm going to move all of this to the side for now. Okay, so let's have the array, but let's use the address now instead. So this is going to be pretty weird, but if I have the address, which would be the first element, the base element of this array. Yeah, so Captain Price is asking, can I just write a procedure to do that work? And you can, and we're going to do that. So yeah, you definitely can, and should, and we will. Okay, so let's print out, but now using just the address. So type, these are now in 32s, and then I did something wrong on purpose. So with this setup, I want to use the address to access the data, but I'm doing something not quite correct on line 12 there. So I get the address in EAX, which as long as I have an offset from there, that's basically the same thing as this value right here. Dereference. Good on Garcevac. Dereference. So I have to dereference that address to get those 32 bits at that location. Okay, and now we're going to look at a couple of different indexed approaches. Okay, so there's the first one. So I'm going to get the second one now. Now we're still calling it element 1, element 2, because that's what we're used to from high-level programming. Okay, so you haven't seen this yet, but you can actually dereference the address and then add the desired byte offset to it. So remember, I have int32s here, so this is one way to do indexed direct, not direct, I shouldn't say that. This is indexed addressing. So add 4, good one. So good catch, Captain Price. Add 4. So you can actually do the offset calculation right inside of the dereferencing. And then I can do, that should have been, okay, tab, and then we'll finish the thought there. So this is indexed addressing, which is the base address plus a byte offset. So this next one will be, so for element 2 is how many bytes over from the base. That one's 8. And then the next one is, yes, I agree, Captain Price. As soon as you see yourself repeating the same code over and over again, you want yourself a procedure. We'll convert this one into a procedure so we can see how to do that. What comes next for element 3? 12, yep, good one. And then element 4, byte offset is 16. Let's make sure that works, and then let's convert it into a procedure. I don't need that guy for a second. So I don't know if you're having the experience that I have, but for some reason this just seems so cool to me. Like I'm down there in the RAM, you know, I've got an address and it's just moving over a number of bytes, and I feel like I really know what's going on at a point. Okay, so there's all my correctly displayed. Okay, so let's fix this. I'll show you first and give us some hints about it. But one thing I can do, in fact, I will do it up here. One thing I can do is I can actually store my byte offset in a register. And then instead of doing hard-coded values, I can take a base and then add a byte offset that I stored in a register. So if I have 0 there, then EAX plus 0 is still at the base. And if I did that, then I would do add 4 to EDX. And then add 4 to EBX. Add 4 to EBX. Hopefully this makes sense to everybody. I'm just replacing the hard-coded values with the register. And doing my indexed addressing that way, off of my registers. And if I keep adding 4, then the offset just keeps getting bigger, right? So it starts at 0, then it becomes 4, then 8, then 12, then 16, and I've got all of my so it still works exactly the same, just to point out to you. Now we can turn that into a procedure. I'm going to call this V1. Okay, so this is sort of just programmer training. Ideally, what I want to do in my programming language of choice is write this procedure assuming that I don't really know anything else about what's going on in the program. So if I were completely blind to everything else that's going on in this program, no one had told me anything about it, and I was just told, you need to give me a procedure that prints an array, then I need to work out a set of parameters that would allow me to do that in this language. The first thing I'm going to need is an address of the array. And when you're just talking about raw addresses, dword is the good HLA data type for that. So I'm going to need an address. I might need, let's say, the size of the data involved, which I'll just say is an UNS8. In fact, let's make that an UNS32. Life will be a heck of a lot easier if we do this. Or let's say it could be a type or whatever. In fact, let's do a type. Okay, so I'm writing up this print an array procedure. If I'm going to print your array for you, you're going to have to give me the array's address. I need to know the data type of your array so that I know how to compute my offsets. Does it need to be 1 byte offsets, 2 byte offsets, 4 byte offsets, or something else? And then the last thing I'm going to need, if I want to make my own life easier, is the size of the array itself. In fact, I'm going to make that argument come second. The size of the array itself, which let's make that, does it matter? I don't think it matters. This just means we can't have gigantic arrays. Okay, so I need to know the address of your array. I need to know how many elements are in it. And I need to know what kind of array it is. Is it int16 or UNS32? So I know if I'm offsetting by 2 bytes at a time or 4 bytes at a time or whatever that is. Okay. So let's start by loading up our address into a register. And then we could let's do this. So if the data type is a type 1, then let's our byte offsets, let's say, so hopefully you're keeping track of this. 8. Remember, like we did last week, my own little code for that. So if you tell me that I'm working with the data type 1, then I know that I need to be moving over 1 byte at a time. So I'm just going to load that thing up. I'm going to use all my registers here, probably. D type is 2. Then I know I'm going to be moving over 2 bytes at a time. And otherwise, I'm going to assume that I'm moving over 4 bytes at a time. All right, hopefully everyone tracked that. So what I have now is I have the array address ready to go, and I know how many bytes to move over each time. Okay, so I'm going to do this as a loop, which is why we have this size thing going on. So so EDX is going to be my byte offset value. EAX and then EBX is the amount to adjust the byte offset value by. That seems like a crazy amount. Hopefully you're following okay. Got the address of the array. I have not the byte offset itself, but how much to adjust it by each time. And then EDX is the byte offset itself. And then finally, I can do a loop. So I'm going to use C as the traditional loop counter register. The reason why I'm using CL is because I'm going to loop that number of times. So CL less than whatever the array size is, and then I'll increment CL each pass. All right, so what in the heck do we do here? So, we're going to find a way to refactor our code here in just a second. Make some space here. Okay, so if D type is 1, ultimately what I'm going to do is I'm going to output, I'm just going to output the value. I'll say that's int 8, right, type 1, EAX plus EDX, because that is my byte offset. I think I'll just put a space after each one to save ourselves some room. That's it, right? And then I would repeat that process for the type 2. Those are in 16s. And then repeat that process for the type 3, which are in 32s. So for the number of elements that are in there, I will print out an element, the array plus the offset. And then after I've printed out each element, before the loop repeats, I need to add, so I need to adjust my byte offset by however many bytes I know I'm supposed to be adjusting by. Now technically I don't actually, I can do this a different way, but I wanted to keep this a little bit cleaner. Okay, so you have an array address, and then you have a byte offset. So I have this loop for as many elements as there are in the array. I will print the element at the array address and an offset, which has started at 0, and then I will add a certain number of bytes to the offset so that for the next pass I get the next one over. And if I do that for the size, then I get them all. Let's try it. Let me not lose this. Okay, so let's try it. How many do I have in there? 5. And then the data type here is a type 3 by the procedure zone reckoning. It's an int32. So in theory that should do it, although I need to add a new line after the for loop. Okay, so that's a lot of stuff. I hope that you were able to sort of follow me as we built up to this point. All we're doing is taking an array address and we are adding a byte offset. That's all we're doing here. This is sort of an intimidating way to go about it, but that's all we've done here is we are printing, we're dereferencing a memory address at some array offset some number of bytes to get to a specific element of the array. Now in theory I should get all of my values on one line here if this still runs, which I guess would be a minor miracle. Okay, so minor miracle, it did work. That is indexed addressing. A base address plus a byte offset, and that's the whole shebang, how to put it together. Okay, we're going to add one more technique, and I'm pretty sure I'm about to run over time, but hopefully you can be patient and give me a few more minutes so we can finish this thought and then get you started on the lab. Okay, so that's the byte offset style, what we just went through. So there's another one, and I'm just going to put this in a file and explain it to you. No. We'll just put it here, and hopefully you can. So let's do another one, but let's call this V2. Okay, so the last one, which in my notes is this scaled indexed addressing. What that looks like is a base plus a byte offset times a scale. So this is a little bit more like what you're used to. What you are used to in high-level programming is the languages are automatically computing the byte offsets and the scales for you. So if you're a C++ programmer, as an example, you just think of the elements as being sort of individually numbered, right? There's the 0th element, and there's element 7, and there's element 23. But what you don't see is that C++ is actually computing the offsets and the scales underneath for you. So remember that when you hate on C++ in the future, that if they weren't doing that automatically for you, you'd be having to mess with figuring out how many bytes is a thing and how much to offset from the base. They do all those calculations for you. But in HLA, you have to do them for yourself. So V2 is going to do scaling. So there is another syntax where we can actually instead of doing a byte offset, we can compute the effective address by the base plus the desired element counter times a scale. So let's look at how this whole thing would change. So in V2, I no longer need EBX, and I no longer need this add stuff. Okay, so for version 2, it's a lot simpler, but what you do with the scaled indexing is you simply multiply this by the number of bytes of the element of interest. So in the case of, I don't know why I did it that way. Okay, in the case of int 8, the scale is 1 byte per element. I don't need EDX either. Let's just get rid of that. We're going to need ECX. So this thing I'm no longer happy with. Let's make this 32 so that we can use ECX here. It'll make our lives a lot easier. Okay, so how does the scaled indexed addressing work? You still need a base address. You need an index like you're accustomed to, so element 0, element 1, and then you scale each element based on the number of bytes the element consumes. So the trick here is, you notice how much simpler it is, because all you have to worry about now is a scale, a base, an index, and a scale. So it simplifies the code a lot to do it this way. What's the scale? How many bytes are in int16 for my scaling factor? 2 bytes per. So this is the last addressing mode that we will do, is scaled indexed addressing. So you take a base, the desired index, and then the scale in bytes of each individual element. So the last one, the scale is how many bytes per element? 4 bytes. Good one. So good one. So that's scaled indexed addressing. This looks weird because you're used to high-level languages doing all that work for you, which is quite nice that they do. But this is how it works on the processor, actually, for accessing array elements, is by computing the address, either by the long way of doing it, which is the base address plus a byte offset, or the slightly shorter way, but still not perfectly easy to understand, array address plus the desired index in the traditional sense times the scale of each element. I wanted you to see also that the scaled index addressing, in my mind, is a lot easier to write code for. It lends itself a little bit better to looping. You can do it in less code. Okay, so let's look at the lab. Hopefully I didn't go too fast, and let's see where the lab gives us an opportunity to practice this stuff. Let me close these things. All right, let me get the lab, and then we're down to just a couple minutes. So appreciate it if you manage to stick around and you're being patient, because I know we say an hour. Raw. Oh, and I know that this thing, like the formatting of this thing is messy in places, and I tried a whole bunch of different ways to clean up the formatting of the lab code, and for some reason this week it's just not cooperating with me. And it's very frustrating. Make sure this goes in my folder. Okay, so the purpose of Lab 12 is to give you a chance to experiment with these new addressing modes. Now I just sort of randomly picked data types for arrays. So let me just show you the setup here. So the first array is called mychars. It is 10 char. A character consumes 1 byte. So that's the important information about this array, is that it is 1 byte per element, which means it's a total of 10 bytes. This 10 dupe z, basically across the 10 elements of the array, it will duplicate the value z. So you get 10 z's or z's if you're from the continent. This is a nice HLA feature which lets you populate your array with something other than zeros. So I just duplicate the z 10 times, and that's how I populate my array. So my chars is 10 z's, 1 byte per z. My ints, 5 int 16, so that's 5 2-byte elements or 10 bytes, and then I've pre-populated it with some data. And then my uns, which are 3 4-byte elements, or 12 bytes total, which I've allowed HLA to zero out because that's its default behavior. So that's what you have to work with. My chars, my ints, my uns is... okay, so let's scroll down and see what there is to do. I've already finished, I believe. Yep, the get char procedure is just done. But you may find it handy in the second individual project to have this procedure. The main difference here is that it uses getC for get char, is its job. And then this is a little HLA trick for ensuring that the input is alphabetic or numeric. So I don't accept anything that's not alphabetic or numeric, meaning I don't accept spaces or punctuation. But if you want to look it up, I found chars is alphanum in the HLA standard library. That's where I got it. That one's done. Get int 16, we had this one last week, and you all implemented your own, but same one. Notice, by the way, we have the get char here because we have a mychars array, so that we'll use that to read data for that array. Get int 16 to read data for the int 16 array, and then get uns 32 to read data for the uns 32 array. Its main difference is that it does get U32s and the typecast for the range fixing or uns 32s. And then I'm pushing and popping a couple of registers here. This is a little bit weird looking, I know. You can't see where I'm using these ECX and EBX, but I can tell you that try and try uses those registers. So to protect the rest of your program from try and try, that's why I'm doing these B and C push and pops. The way I figured that out is through experimentation. So when I didn't have those there, it broke stuff. I did the same thing with the try and try and the get int16. Pushed the B and the C and then popped them in reverse order because through experimentation I discovered I had to. I did the same thing for get uns 32 because I had discovered through experimentation that if I didn't do that, something broke. Go again is already done. Okay, so printing. There's something new here, and you have to be careful about your use of this thing. But in the case of the print function that does not return any values, push AD, what that does is it actually pushes all of the 32-bit general purpose registers all at once. So it can save you time to push all of the D-word registers and then pop all of the D-word registers. That is safe to do for print. It is not safe to do for any of the get functions. So don't do it for the get functions because you need the EAX to come back. Okay, but it is safe to do it for the print function. You can push them all, pop them all, and save yourself some extra lines of code. Okay, so here we go. Copy address into EBX, so we know how to do that. That's the parameter address. So you can't use addresses unless they're in registers. You can pass them in variables, but you can't actually dereference them unless they're in registers. Okay, so load up the address, this time in EBX per the instruction. The for loop was already written, but you've seen this now before. You can guess where that came from. This first one has already been done for us. So this one's using scaled indexed addressing. I bet I don't have to do that for you guys. I bet you can figure that second one out. And I've already kind of left breadcrumbs there about the base, the desired index, and the desired scale, but this time for int16, this time for uns32. So the trick is to make sure that your typecasts are correct. Char, int16, uns32. So make sure your typecasts are correct and make sure that your computed or effective addresses are correct. But you can do those. Edit cell. Same idea. I'll do one just to be sure that we're okay. So I'll do this one. So get int16 and we'll do like between I don't know. Okay, that's going to bring back AX. So this one's tricky, and you have to pay attention. So let's work it out, and you'll notice because the program won't work. So I want to explain to you why this char one is how it is. So technically, I should say the scale here, because this procedure is assuming a scale. Why do you think I could get away with the scale not being there? So for some reason, this one would allow me to get away with the scale not being there. Why would that be? Because it's 1. So when the scale is 1, it's optional because you're just multiplying it by 1, which doesn't change anything, right? So the reason why that one didn't have times 1 is because it doesn't have to have it. If you're scaling by 1, it doesn't change anything. But in this case, so now my input value comes back in AX because it's 16 bits, which it tells me about that. So the trick now is what goes here? And is this last part optional? So what goes in the first slot? And you can say it by its actual register or by the word that describes its meaning. EBX, perfect laser, that's the base. Now to figure that out, you have to sort of look around a little bit. Oh, in fact, we were supposed to have done that up here on number 4. So that's why number 4 is there, is to get the base. So the base plus an index. So what register has the index in it? ECX, lasers on top of it. And then what's the scaling factor? Two. Perfect. Scaling factor at 2 because these are in 16s and the scaling factor is 2. That is not optional, right? If you take away the times 2, it does break. If you take away the times 1, that's because multiplying by 1 is the identity, but multiplying by 2, that matters. Okay, so you're going to do a get something here, and then you're going to do a move EAX here. And I think you guys know what to do with that last one. Remember, this last one is uns 32s. So base, index, scale. I'm pretty sure you know how to do that one. Let's see what else there is. Call print procedure. What is on what? Oh, just says pass. Okay. Call print. Is it just called print? Yep, print with an address, a size, and a data type. So this print, we're going to pass through the address. We're going to pass through the size. And we're going to pass through the D type. So that's nice. Because all we have to do is just call that procedure with the same parameters, and it turns out in the same order, so that's pretty easy. And then we call edit cell. And I'm betting, if we look at edit cell, address, size, D type, so we'll just pass through the same address we got, pass through the same size we got, pass through the same D type we got. So I did those for you, but those are boring anyway. So that's the edit, is just, you just have to take your own parameters and pass them through to another procedure that will use them for something. There's a lot of code in here for the second project, by the way. The print, it's not quite the right data types, but they're way huge steps forward, so consider keeping them around. What's 9 and 10? So 9 and 10, just for my, oh, this is just, I guess just an experiment. Oh no, it's meant to be mirror these, right? So call edit array. So this time I'm going to pass the address of my uns array, which it told me to do. That has 3 elements in it, and the code, the data type code is type 2. So that mirrors these things. Those were followed by a new line, and then print all 3 at once. So you're going to have a print my chars. Print needs the size and the data type, so my chars is a size 10, and the data type code is 0, and then you're going to do 2 more prints for the other 2 arrays. So I think that leaves enough to be interesting in terms of a challenge. But if you get stuck, go on Piazza or send me a Canvas inbox. Thank you a whole bunch for sticking around while we went long. I think this is some of the more intimidating material we've dealt with, so making sure that we spend quality time over it is, I think, important. Anyway, hopefully I have armed you with everything you need to be successful on the lab. Please do something to make note of the fact that we are starting to accumulate a lot of procedures that can either be directly used in the second project or can be tailored to fit into the second project. Okay, so the question, what does D word stand for? So D word where is one? DWord, if you'll notice it's green. So DWord is an HLA data type. It stands for double word. And a double word is 32 bits. So the DWord is the HLA data type for 32 bits of raw data. And I say raw data because that is as compared to UNS 32, which is 32 bits. But this is 32 bits that has a type associated with it, which is decimals. Right, so UNS 32 is unsigned decimal integers, whereas DWord is raw 32 bits. So it's a data type. D type is simply an argument name. So notice it's in black. That's just a parameter name. So it's the name that I choose. I could have used, you know, like sneakers if I wanted to. That's just a label that I chose. And I just meant the data type code. So that's just the label that I chose to associate with the parameter that tells me what kind of data I'm looking at. So we have 3 different arrays, and I need to know in my procedure, are they giving me the address of a char array, or the address of an int16 array, or the address of an UNS32 array, to match the arrays that I have in the program. So hopefully that answers that adequately. So data type, DWord, and it's green, which is the tip-off, 32 bits of raw data. D type is just a parameter label that I chose to represent my code for which array is it. Is it the char array, is it the N16 array, or is it the UNS32 array? I did the same thing in my edit cell procedure. So the address, that's the label I chose, is a DWord type. The size, the label I chose, is an UNS32 type. The D type, the label I chose, is an UNS8. So this is the address of the array, the number of elements in the array, and which of the 3 arrays that we have in our program are we talking about here? The char, the N16, or the UNS32 array. So I need all that information to figure out what to do in the procedure. Okay, any others I can answer before we shut down? Thank you, appreciate it. Excellent question. Thanks everybody for participating. I appreciate it. It helps me a lot to know that you're out there. This could be a lonely business. So I hope you have a great week. And I will see you in week 13, which is a week from today. So anyway, I hope the rest of your day is good. I hope the rest of your week is good. And just get in Piazza or get on Canvas Inbox if you get stuck on something. Otherwise, take care. Have a good week.